Hi, my name is Darshini, and this is Physics 2212 11.5. So a little introduction on this lab.
Um, we are collecting observational data of a magnet falling through a conductive tube of aluminum foil, modeling the magnet/tube interaction computationally, and comparing the computational predictions with observed data. So for our key concepts, we have Faraday's law and Lenz's law, which are represented on that left side, and then Biot-Savart law, which is represented also on the left on the bottom. We also have the time derivative included, and Newton's second and third laws. The assumptions are that the bar magnet is equal to the magnetic dipole, air resistance is negligible, and the only forces acting on the magnet are gravity and magnetic forces. So here's a summary of the results. They're pretty similar, 1.34 seconds versus 1.38 seconds. In the system and the surroundings, for the system, it's the aluminum foil of the bar magnet, and the surroundings is the environment. So on the left, you can see all the trials that were done experimentally, and the procedure was basically to set up a magnet, have it fall through the tube, and record the time in which it took to fall. And then the measurements are also shown here, and these will be plugged into the flowchart. So for our checkpoint questions, why can't we use ferrous tube, for example, steel pipe? The reason that you can't use ferrous tube specifically is because it's iron, and iron is one of those elements that are more magnetic, and so it could possibly interfere with the magnetic field already created by the pipe. And then what happens to the magnet? How does it compare to the magnet falling through space? The magnet is falling at a slower pace than the magnet. And here's the glow strip coding. So from the coding, this is what we got. We got the
Computational model. On the left, you can see the velocity versus time graph, and on the right, we can see that the time in the tube was 1.38 seconds, and the model is displayed on the right as well. So kind of from this picture before, you could see the red and the blue. So based on this, what color corresponds to the clockwise and what color corresponds to the counterclockwise. Counterclockwise goes to the red, and the blue is the clockwise current. And we can see this because of Lenz's law. Then what happens to the dynamics of the system when you flip the magnet around? The system is basically going to act the same, but it is going to restore the direction of the magnet. And then how does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be more accurate? So I would say, excuse me, that they were pretty accurate, and the computational system was a little more accurate because there is more representation of ideal situation. So maybe like the air is not interfering with the system, or other possible variables that could affect it. How does the shape of the velocity versus time plot tell you about the forces acting on the bar graph? So this velocity versus time plot shows you kind of the imbalance in forces, where the velocity is in the beginning more responsible for the force. Then as you hit that plateau, there's an equalization of forces, and then towards the end, you see that going towards the zero, there's more gravitational force. And so overall, the results were generally similar. Both of the experimental and computational models reflected that the aluminum foil is slower than free-falling space. And so from this, if the resistivity of the conductor were reduced as low as possible to zero, the falling magnet would fall less effectively and honestly might not even fall through the pipe. And then if there were holes or slots cut into the tube, this would disrupt the magnetic field that's made in the tube, causing more likely causing the magnet to fall faster. Thank you for watching.